This video is sponsored by Stellarium Mobile Plus. Made by the original creator of the award-winning Stellarium Desktop Planetarium, Stellarium Mobile Plus puts 1.6 billion stars and 2 million nebulae and galaxies at your fingertips. Planets are rendered in high-resolution textures, and the night sky can be viewed in beautiful 3D in real time from any location on Earth. I'll tell you a little bit more about Stellarium Mobile Plus at the end of this video. The black holes we've detected so far fall into two categories. Stellar mass black holes are often found in binary systems with masses equivalent to 10 times our Sun. Then there are supermassive black holes, which dominate the centers of galaxies and weigh millions to billions of solar masses. Somewhere between these extremes must be intermediate mass black holes, with masses ranging from hundreds to hundreds of thousands of suns. Models predict they should reside in the centers of dwarf galaxies and possibly globular clusters. But so far, they've avoided detection. But now, after years of investigation, a team of astronomers using the Chandra X-ray, XMM Newton, and Hubble Space Telescopes made the most convincing detection yet of the missing link of black hole evolution. A 50,000 solar mass black hole devouring a star a long time ago in a galaxy far, far away. Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. Finding black holes is hard to do because they are black. They greedily consume light and never radiate so much as a single photon back into space. The only way we can detect black holes is by detecting the radiation coming from just outside their event horizons. For example, we've detected stellar mass black holes in binary star systems. If the two objects are close enough together, matter can flow from the companion star into an accretion disk surrounding the black hole. The disk feeds the black hole, but as it does so, it heats up to millions of degrees, producing X-rays. Cygnus X1 was the first black hole discovered. It's caused by a blue supergiant star losing mass to a 15 solar mass black hole. We've detected several stellar mass black holes this way, both here in our galaxy as well as in nearby galaxies. Then there are the supermassive black holes that live in the centers of galaxies, including our own. Sagittarius A star holds court in the center of the Milky Way. At 4 million solar masses, it occasionally feeds on clouds of gas, generating X-ray and radio emission that penetrates the spiral arms that would otherwise block its view. The black hole at the heart of M87 was initially revealed by a 5,000 light-year long jet of plasma, hurtling toward us at nearly the speed of light. Then it was imaged directly by the Event Horizon Telescope. This black hole is 6.5 billion times the Sun's mass. Despite their extreme difference in mass, all black holes follow a simple rule. The greater their mass, the larger their event horizons. For example, to make a 50 solar mass black hole, you'd need to squeeze 50 suns into a ball less than 300 kilometers across. M87's black hole is the equivalent of 6.5 billion suns squeezed into a ball about the size of our solar system. But if the universe can have supermassive black holes, then that must mean it has to have intermediate mass black holes, right? Well, not necessarily. After all, nature is under no obligation to make sense to us. However, it seems that intermediate mass black holes are needed to solve a problem with the formation of supermassive black holes in the centers of the earliest galaxies. These black holes consume enormous quantities of gas, and their accretion disks shine with the light of up to 1 trillion suns. They're so bright we can see them from across the universe as quasars. Because of light's finite speed, we see quasars when the universe was less than 1 billion years old. The most distant quasar known is ULAS J1342 plus 0928. This quasar emitted its light when the universe was less than 690 million years old, yet its supermassive black hole is estimated to be 800 million solar masses. So how could such a massive black hole form just a few 100 million years after the Big Bang? At first, it might seem that it started out as a stellar mass black hole that just grew up as it fed on the surrounding matter. But there's a problem with this hypothesis. Remember that accretion disk that we talked about? It puts out a lot of radiation, so much that it exerts a strong pressure on the surrounding disk and pushes it outward. Some of it still manages to find its way onto the black hole, but it's at more of a trickle than a torrent. Therefore, it might take a stellar mass black hole up to 30 million years to double its mass through normal accretion. Even 700 million years isn't enough time for a supermassive black hole to grow from such a small seed. In order to form supermassive black holes while the universe was still young, they would have had to have grown from much larger seeds, black holes in the 100 to 100,000 solar mass range. Fortunately, the conditions in the very early universe allowed such black holes to form pretty quickly. A couple of 100 million years after the Big Bang, the universe was a dark cloud of hydrogen gas. With no heavier elements to arrest their flow, hydrogen was free to rapidly collapse into ultramassive stars that weighed hundreds to up to 1,000 times our Sun. These stars would explode as hypernovae after just a couple of million years, producing violent gamma-ray bursts as their cores collapsed into black holes hundreds of solar masses. In fact, some of those first stars got so massive, they seem to have skipped the going supernova altogether, and their entire mass just imploded into a several hundred solar mass black hole. In fact, some of those hydrogen gas clouds may have collapsed so quickly they may have just gone straight into a black hole weighing 1,000 solar masses without ever bothering to form a star. Such black holes would have been born into a buffet of hydrogen, helium, and nearby stars. Soon they'd occupy the centers of the first proto-galaxies, which would quickly merge with others. Their central black holes would soon find each other amid the chaos and merge into the supermassive black holes we see today, while entire galaxies grew around them. But not all of these intermediate black holes would merge. Countless proto-galaxies still exist today, we just call them dwarf galaxies, and they presumably hide intermediate mass black holes in their centers. However, most dwarf galaxies are devoid of gas, so their black holes are less likely to continuously feed and emit radiation. This is what makes detecting intermediate mass black holes so difficult. But if we're lucky, we might be able to catch a black hole shredding a passing star. If a star comes too close to a black hole, tidal forces increase until the star can no longer hold itself together. The star shreds and encircles the black hole, heating up to hundreds of millions of degrees in the process and unleashing a flood of X-ray radiation. This is called a tidal disruption event, or TDE. TDEs are rare, occurring only once every 10,000 to 100,000 years in our galaxy. But they create hyperluminous X-ray events that can emit up to 1 billion times more X-ray energy than the Sun. That makes them bright enough to be detected even in distant galaxies. If we can catch one of these events, we may be able to determine if a black hole was involved and weigh it. TDEs have a characteristic light curve of an almost immediate outburst that holds steady for a couple of years, followed by a long gradual decline in X-rays over time. Several intermediate black hole candidates have been detected in dwarf galaxies and even in some globular clusters from X-ray events that were thought to be due to TDEs. But as we'll see, the X-ray light curve produced by a TDE can also be produced by a cooling neutron star. In 2006, a hyperluminous X-ray event called 3XMM J215022.4-055108 was detected by the X-ray Multiple Mirror Newton X-ray Observatory. The name's a mouthful, so I'm just going to call it J2150. Anyway, it seemed to originate in the vicinity of a galaxy about 800 million light years away. A team of astronomers led by Da-Chien Lin at the University of New Hampshire discovered the event in archival data from the XMM Newton and Chandra X-ray observatories. Now, a previous image of the primary galaxy was made by the Hubble Space Telescope in 2003. It revealed an optical counterpart to the X-ray source, which appeared to be just slightly off-center from the exact location of the X-rays. Lin's team made follow-up observations with NASA's SWIFT satellite in 2014 and then with the Chandra X-ray Observatory in 2016. These observations showed the X-ray flux had decreased at a rate that was consistent with a tidal disruption event involving a black hole weighing 50,000 to 100,000 solar masses. That's an encouraging result, but the same X-ray cooling curve could also be mimicked by a neutron star in a binary system. If its crust were heated in a large accretion outburst, it would create an X-ray flare similar to the J2150 event and cool off in the same manner. Still, Lin and his team had good reason to believe that this wasn't due to a nearby neutron star flare-up. For one thing, the source appeared to be right next to a large lenticular galaxy dubbed Gal-1. Several smaller galaxies appear to surround it, including a slightly larger dwarf called Gal-2. These two galaxies appear to be connected by a stream of gas and stars that was stripped off Gal-2 as it was tidally disrupted by Gal-1. But proximity in the sky to a galaxy isn't proof that it can't be a nearby neutron star photobombing the image. If the source of the J2150 event were a star, it would appear as a point source, but a small galaxy or cluster would appear as an extended object. Unfortunately, the 2003 Hubble observation was designed to really image the Gal-1 galaxy, not the J2150 source. So there wasn't any way to determine if the source was a dwarf galaxy, a globular cluster, or just a fuzzy image of a foreground star. To settle the question, the Hubble Space Telescope observed the galaxy once again in 2018. The difference from 2003 to 2018 might not seem like much at first, but the 2018 image was a huge improvement, allowing the team to resolve the source as a compact but extended object. J2150 was extragalactic. Accounting for the object's apparent brightness and distance, Lin's team determined the source was roughly 176 light-years in diameter with a mass of about 10 million suns. That makes it more likely the remnant nucleus of a tidally stripped dwarf galaxy than a massive globular cluster. The new observations allowed the team to refine their measurements of the X-ray spectrum of the flare. They found it was caused by a 50,000 solar mass black hole shredding a passing star. This makes J2150 the strongest intermediate black hole candidate found to date. We may have finally found the missing link in the evolution of supermassive black holes. And that in turn will help us to answer questions like, what came first, the galaxy or the black hole? Or did they both show up together? Our best chance of answering these questions will come when the James Webb Space Telescope launches sometime in, well, who knows at this point. But even though some science has been delayed, it hasn't by any means stopped, and neither should you. The night sky still calls to us, which is why I invite you to step out every now and then and see what the universe is doing. In fact, it's super easy to navigate the sky with Stellarium Mobile Plus. I've been using Stellarium Desktop to depict the night sky here on Launchpad Astronomy and in my classroom, so I was very happy to learn that I can now take it with me when I'm gazing at the sky at night. To that end, you can switch to a night vision mode, zoom in on planets, galaxies, and nebulae. You can track planets and even satellites as they pass overhead, all while experiencing the most realistic depiction of the night sky. And if you're an amateur astronomer with a motorized telescope, you can control it using Stellarium's built-in telescope server protocol. You don't even have to have an internet connection. Stellarium Mobile Plus puts Stellarium's elegant combination of power and simplicity into the palm of your hand. It's available on Apple's App Store and on Google Play, and I invite you to download it today. I'll have a link in the description below. My thanks to my patron supporters for keeping this channel going, and I'd like to welcome my newest patrons, Lucas B., Tom Carlson, Douglas D. Farron, Simon Hallman, and R.J. Johnson. And as always, I'd like to thank my cosmological supporters, Michael Dowling and Stephen J. Morgan. If you'd like to help out for the price of a cup of coffee every month, head on over to my Patreon page. And if you'd like to join me on this journey through this amazing universe of ours, please make sure that you subscribe and ring that notification bell so that you don't miss out on any new videos. In the meantime, stay home, stay healthy, and stay curious, my friends.